Hello everyone, welcome back to my channel, Black Box Engineering. So I'm going to get into making this a actual usable subcircuit and maybe even cover potential expansions, because for those who aren't aware, there are ways to model all the other normal gates like the NOT, NOR, OR, and exclusive OR. All those other gates you can model them through different combinations of NAND gates and whatnot. So I can maybe show kind of how that works, because in this software you can make subcircuits of sorry, let me rephrase. You can make subcircuits with subcircuits in them. It's rather neat on what you can do in this program. So anyway, so we're going to just use the MOSFET model to do this, just to make sure that you understand the minimum amount of information that you need. Again, is length and width, KP, gamma, phi, lambda, and VTO. And I did find out at least one piece of information. VTO is the voltage bias within the transistor. So that's where that 0.7 comes from. Everything else I'm not entirely certain about, but I don't really have a lot of time on my hands to figure out what those are. Maybe at some point I can look into it, but anyway, so the positive MOSFETs at the top both have the same length and width. The top MOSFET on the bottom has 1 micro, 50 micro, and then the only one that changes for the length and width, just for the width side, the negative MOSFET on the bottom is 100 U micro for the width on this one. So I'll put that in the description so I won't have to explain it again. So anyway, so now that we have this kind of setup, we can add inputs and outputs and voltage sources. So clearly logic gates need some kind of power, so we need positive power and negative power, and usually this ends up being ground. So the best way that I like to set it up is, oops, not that one. Might as well call voltage and input. It's not technically one, but I'm going to call voltage input VSS. That's very common on electronic data sheets. No, sorry. That's wrong. Is it? No, hold on. Give me 1 second here. Sorry, no. It's VDD. I always get them. It's been a while since I've actually seen a technical data sheet with the power, but yeah, VDD and VSS is the proper distinction. So I'm going to call this one VDD, and then I'm going to need the negative sides. That's the VSS. Again, I guess we can call it an input, even though these are technically bidirectional in some way. And then we need an output, so just call it out. And then we need our A and B inputs, so A input. I'm just gonna, and our B input. So this is all the tags that we need for our circuit, our subcircuit. And I should probably briefly explain for those who aren't, when you get into complex diagrams, for the most part, anything with little dots or bigger intersections like these indicate that they're nodes, and anything that you see overlap, because people don't draw those little bridges over things anymore. Professionally, it looks a lot better than having a little curve over here to indicate that this wire is jumping over this wire. In the engineering world, you will just see a bunch of intersecting wires like this with no node mark. That means that they're not actually a node, but rather that they jump over each other. It's implied. So that's something I should probably should have explained a little bit. So anyway, now that we have this, we can save this as a NAND. Okay, so now that we have that, we should probably make a symbol for it too. So let's just open up File, New Symbol, and we're going to set it up pretty much just like a normal NAND gate. So we need lines. I changed up the color scheme of my setup so that this could a little bit neater. So you know, well, can I put pins? I wonder. Anyway, so we've got our body of our rectangular looking part of the NAND gate. Now we just need an arc. So draw arc, and I think you start in the middle, or maybe at the end point. Kind of forget how to. Okay, maybe start the middle here. Nope, it's been a while. Let's try this point, and then just kind of drag it till it looks like it's touching both things. We're gonna start the arc here and end it here, and then let's draw a little circle. And then move that to the center. Draw another line. I just need to make sure that I'm on the grid in certain spots. The spacing between these are set. I've never figured out how to change that. Technically, there are sub points between these, so let's add our pins. For this method, we need to make sure that the pin names are the same, but netlist order does not matter. You'll see why. So we need. Oh, I forgot to add power. I need power. Let's just make lines. Oops. Because we need our VDD and VSS ports. So VDD, come on, VDD. I guess right is fine. And this is kind of where it gets a little hard to place like text, because it might not look the best, but it'll be fine. Okay, I left these lowercase for the other parts, and then we need a pin on the bottom, if I can remember to. Let's have these right, or I mean left aligned, justified, I should say. Then we have our output. And we can kind of nudge this. That looks okay. It's not the best looking thing ever. Just know that output is referring to this little spot here. All I did is I changed it to top justify, and then I used this offset to kind of make it look a little bit better. It's not perfect, but it's fine for what I'm doing. So then I need the A, left justify, Oh shoot, these have to be on the grid. Okay, that makes it a little bit harder to do. I mean, I could always bend them. It's fine. To make it'll look a little strange, but you know, actually, it wouldn't look too bad if I made it like in between and then angled out kind of like this. That wouldn't look too terrible. I mean, I could even, instead of doing, actually, now that I think about it, why not just do kind of like a wire? Oops. Didn't draw that line long enough. When it comes to drawing symbols, it is a little bit more particular than doing wires, so dang it, I keep on missing the grid points. It's pretty precise. So anyway, it'll look a little goofy, but that's fine. Let's do bottom justify. And then we need B top justify. So that it at least kind of lines up with the lines at the end here. And it leaves room for wires and stuff, so this doesn't look too bad. I wish that, I mean, I could have scaled up the symbol a little bit, but whatever. This will work just fine. I'm sure that you'll be able to make better symbols than I do, so it doesn't really matter that much. It kind of bugs me. So now we save this as a NAND .asy, like so, and then I think it's technically just ready to go as is, and this is kind of why I like this method a little bit better, at least for LTSpice. I forgot to mention in that other video that the other method, the netlist method, it will be pretty much compatible with any spice simulation program. There might be some adjustments you have to make, because I don't know if LTSpice has special flags or not, but that method is supposed to be consistent across all spice. So that's another huge difference between these methods. This method won't work on other spice programs because this is specific to LTSpice. So anyway, now that we have our symbol and our circuit, we can oh, I forgot. I almost forget this every time. We need an attribute thing. So to do that, we right click, do attributes, attribute window, instance name, and then just kind of, I guess I'll just place it here. This can be moved around in the actual program when you place it. So then new schematic to use this anyway, and we open up our little folder, click the NAND, place it, and it should run without problem. So let me just do 5 seconds. Oh wait, yeah, needs ground. So let's see. Yep, okay, that works. So anyway, we've got our symbol in here now with proper pins and whatnot. If I actually right click this and then I say I want to see the symbol or schematic, I can actually click it right here and it'll take me right to the circuit inside LTSpice directly. It's really cool. Kind of helps you troubleshoot if you, let's say if you, I don't know, like I think I left this bottom one as a PMOS earlier and I was getting wrong values for my voltage readings. You could be like, hey, this isn't turning out quite right. Let's see what's wrong with the schematic. Then you go over the schematic by saying, let's look into there. We find the mistake, correct it. We can save right in this instance, and it will save the master file, and it will fix it right away. That's a benefit of doing it this way. So now that we have our model, I'll actually show that it actually works here. So let's just do like a very basic logic gate test. That's an easy way to make sure that this works. So let's add a voltage source. Oops. And let's just make it 5. This is for power, so connect this to the VDD. We need a ground on the other side. Ground for this side. And again, remember, these are connected. Even though they're separate, they are connected. So good way to test these is to set up like 2 voltage sources. And then, of course, we need to monitor the output. So we need 2 voltage sources here. Source A, source B. We need to ground these together. Okay. So let's make these pulses, like specific pulses. To do that, you right-click the source, and I'm going to use something called a PWL. It's just pulse width length file. No, sorry, not this one. This one, PWL with exact voltages. What we want to do is set up like the 00011011 truth table. To do that, we need, let's say that I should probably name these. Let's call this, oops, VA, oops, VB, let's call this VSRC, just to be consistent. I mean, I could call this VDD, but whatever, not to confuse anyone. So anyway, so let's get back. Advanced PWL. So for the first time, we're gonna set VA as 0 volts to begin with. So at time 0, we're gonna have 0 volts, and we're gonna keep it 0 volts for half a second. So that means it still needs to stay 0 at half a second. You'll see why. And then 0.1 seconds after 0.5, I should say 0.01 seconds after that, we need to swing it to 5 volts. So we've got that so far. I'm going to move this. VB, advanced PWL. Time 0, we want 5 volts immediately. We need it to stay on for half a second. So at 0.5 seconds, it's still going to be 5 volts. At 0.51 seconds, we need it to swing down to 0 volts. Okay. And I just kind of edit these in parts so that I kind of can figure out how this flows in my head. So since we want it to stay on for half a second, that means that 1 second in, it needs to stay at 5 volts. And then I usually just do 1.1. I think it needs to stay at 5. So 0.5 stays at 5. swings to 0 at 1 second. Sorry, at 0.99 seconds it needs to be 0, and at 1 second, oops, 1 second it needs to be 5. 5. And you just click additional PWL if you want to add more points. So you'll see why I structured it that way. So if I were to, let's just not hook this up to the NAND gate yet. Let's just run this as is. So yeah, on VA we'll see it start at 0. At half a second it shoots up fast to 5 volts. That's if I were to leave it, let's say if I were to go from 0 to 5 at 0 seconds at 0 volts and 5 at 0.5 seconds at 5 volts, it would do a linear like ramp up to that. I need it to turn on quickly, so that's why I did all those 0.01 changes. So 0, 0.5 it goes to 1, 0 is at 5, so that means 5 and 0 should make an output of 5. And then on voltage B, we're going to see it swing down to 0, but this is going to swing up to 5, so we're going to have a 1 and a 0 here. So a 1 on voltage, I should probably name these. Okay, so this is VA. Yeah, so VB 1 0, VA 1 0, and then they both end up being at 1 at 1 second, producing a 1 1 or 5 5. Again, 1 and 5 are the same. 5 volts and 1 in digital 1 we consider the same thing in this case. So this should give us all the different cases for the output. So now if we hook it up, let's exit this. So we treat this as source A, source B, clean it up a little bit here. So we've got our input like this. Our output should be 1 1 0, and it technically starts to swing down to 0, but since it's so fast it goes right. This transition between like right here, it bounces a little bit because it's not the 0.01 second slope is still technically not fast enough. It gets complicated, but that's why that we see a tiny dip right here, but it swings right back up to 5 volts. And then as soon as we see a 1 1 case, we should see a 0 volt or very nearly 0 volt. 698 picovolts. That's basically 0. So yeah, there we go, a NAND gate. Created in LTSpice and making an actual subcircuit, because having this is a lot more neat and small than having this whole thing connected to voltages and stuff. We're saving space by making these symbols, and like I said before, you can now make other circuits using these subcircuits, and it just goes deeper and deeper. It's really cool. Like if I were to model, let's say if we want to make a AND gate, we can totally do that. All that we need for that is you need to put a NOT on a NAND gate. That's really all that you have to do. So let's just clear everything here now that we tested this. Alright, so now that we have this, let's just pull in an inverter, because this is LTSpice's. I mean, technically you can make your own NOT gate as well, but you know, I'll just show you how to do that and make an AND gate as well. So a NOT gate is you just tie the inputs together, and you make it one input by tying the inputs together. So like this, and then there's your NAND gate. The reason that this works is so if you were to provide a 0 on the input side, both zeros make a 1 for a NAND gate, so 0 to 1. And since two ones, 1 and 1, NAND 1 and 1, you get 0, 1 to 0. That's literally all that you have to do. We need these as well. We need everything that we need before. And our output. So our input, our one input now, I'll just call it A. So this is kind of where it gets confusing. These letters are tied to the symbol, but they're not actually in the circuit. It's a little hard to describe, but it'll make more sense as I draw this. So we also need the VDD VDSS. So oops, I keep on hitting the wrong thing. VDD. Oh my gosh. VDD. Again, I'll just call them inputs. VSS. So this is our NOT gate circuit. So then we just do File, Save As, NOT. Since I already have one, it's just going to override it. Oops, ASC is I'm going to override it. And then let's just make a quick symbol. So File, New Symbol. Let's just do lines. Let me get a little bit bigger, just to make it nice. Add a little circle, because that's how NOT gates look. I don't really care if it looks perfect, honestly. We need our lines for power, undo, so we got all of our stuff here. VDD, right, justify. Let's just do another pin, VSS, right, justify, out, top. Let's bring that in a little bit with the MOSFET, the offset. Oh my gosh! And then we need, what was it again? A. P, top justify, oops, A, and again offset, if I can speak today. Let's see, this was 2, might as well make it even. So there's a very simple like visual for our NOT gate. File, save as, not.asy. Oops, not knots. Should just be not. Yes, I want to replace it. And if I were to, again, test this, because it's always good to test your sub-circuits. LTSpice, not. We need our source. I'll probably do separate videos for the other gates. Maybe not one per, but we'll see how I am. I just know that I won't be able to fit it all in one here because I don't want to go too long with these. So source 5. Let's add another voltage source. If I can put it the right way. This one is just easy to say on and off. In fact, I can just do a pulse. 0, 0 for, I don't know, like half a second. 1 nano. I think that's all that I need. 3 seconds. I need one more. Okay, so there's our little pulse here. I can close these out. So we should see the opposite. So from 0 to 0.5, we should see a, right, that's 0.5, right? I think so. Yeah, 0.5. 0 to 0.5, it's 5, and then it turns off, and then it turns back on. So there's a NOT gate. And it goes through multiple steps this time. It's rather cool. It comes in, goes through this schematic, through this MOSFETs. So in a step, and it still works very fast. It's very fascinating, very cool. And I think I'll probably end up just stopping it here. So yeah, we made a NOT gate and a NAND gate sub-circuit out of MOSFETs, and then the NOT gate is a sub-circuit that contains a sub-circuit. So yeah, it just, you can do all sorts of things with this program. It's very cool. Anyway, thanks for watching, and I'll see you in the next one. Like, comment, subscribe, and appreciate the support I've been getting. And yeah, see ya.